Hi everyone, my name is Yuan Kai and I'm a postdoc at Fudan University now. And I will be presenting our paper MetaSQL, a generated and rank framework for natural language to SQL translation. So firstly, I would like to start with the definition of about natural language to SQL problem firstly, as I suppose some audience here may not be familiar with this task before. So what is the natural language to SQL problem, which we call to SQL problem shortly? I believe this problem is pretty straightforward by given an ad hoc natural language query for a structured database schema, and the task is to generate the corresponding SQL query, which may further be executed to the database to get the query result. So you may notice that this task is kind of similar to language translation task. Yes, one of the most the mainstream approaches for natural language to SQL problem is using the sequence translation model. So based on this framework, the common way to do that is to encode the NL query using the encoder part, and using the output part, decoder part, to output the sequence token by token. And depending on different approaches to embedding or to encode the database schema, so they may using different encoders to embedding the database schema, or using the sense encoder as the natural language query. So anyway, this is the whole picture about the sequence model for natural language to SQL problem. And to further leveraging the existing pre-trained language model, most sequence model may use PLM to further enhance their language understanding ability. Another mainstream approaches right now, I think since last year, is rapidly emerged, is about large language model. And I have to say, large language model makes pretty much easier for doing the natural language to SQL problem at this moment. So as you can see, you may using the out-of-the-box large language model to do the NL to SQL problem directly, or just using your own data to fine-tune the large language model to get better results. And anyway, to either using out-of-the-box large language model or fine-tuned large language model, so they may using in-context learning technologies to do the inference. So as you can see, this is an example from another paper. I think is very clear here, and to doing how to serialize the database schema, and how to concatenate with the natural language query, and to fed into the large language model to get the pretty good result. So what you need to do, I think the most important part is the thoughtfully crafted prompts that you have to make before doing the large language model inference. No matter for the sequence model or large language model, I think the mainstream approaches primarily use auto-regressive decoding paradigm to generate the SQL queries or SQL sequences. So let me give you some more clarification here. So what is auto-regressive decoding? This is kind of a decoding strategy where to generate the output sequences one element at a time. And when you generate an element, so the model can leverage all those previously generated output tokens to generate this step element. So this is what auto-regressive decoding. So yes, I think auto-regressive decoding, this kind of decoding strategy has some problem. So which may make the NL to SQL not very perfect. So I think we summarize into different main aspect. I would think the first one is lack of the output diversity, which means this kind of decoding strategy mostly or commonly use bin search or other sampling methods to generate the output sequences, and which may tend to exhibit repetitiveness on the output sequences. As you can see, this is an example. Oh, sorry, this have um, some problems with the people side. Anyway, so this is a kind of it's an example. So when you're giving a natural language query, what are the country codes for countries that do not speak English for an existing auto-SQL model, and when we check the Bing search result for the top 1 to top 5 SQL output, we can find those highlighted, the bold font, front or duplicated, right? So there are many great repetitives on the output sequences. And another one is we think is due to lack of global context awareness. So what is global context awareness? I think due to the incremental nature of this kind of strategy. So when they generate the output sequence or sequence token, and they can only see the previous history, right? This is the partial context we think, and they cannot see the future tokens. So only partial tokens is considered for this kind of decoding strategy. Okay, so this is the two main problems that we think in the current vanilla auto-regressive decoding strategy. So we're thinking, is it possible to develop a unified framework for all those either sequence-based model or large language model and auto-SQL models to improve their vanilla auto-regressive decoding? We're wondering if this is possible, and we think the answer is yes, right? So this is why the MetaSQL comes. So what is MetaSQL? This kind of an L2 SQL problem using the MetaSQL injection. So we introduced query metadata to help to improve the overall translation process. So this is overview for our framework, and which includes mainly three phrases. The first one is the semantic decomposition, and second is the metadata condition generation, and the last is the learning to rank phrase. Okay, and I will go through each phrase in the next couple of slides. Okay, so what is the decomposition? I think this phrase is kind of interesting because we are inspired by the practice, coding practice I have done before in some public platform. And for each coding problem, we think each problem has some problem tag, which will tell you how difficult it is for the coding problem and what kind of algorithm you will use to solve the problem. So we think the text or the metadata, we think will be much helpful for us to solve the coding problem, even though it is hard, right? So we're motivated by this, and we decompose the NL2 SQL process into NL2 metadata first to get a set of necessary or very important query metadata. Okay, so this is the cogredient semantics that we have to capture firstly, and we will do next for the SQL translation. So we in this paper we defined three different metadata type. The first one is operator tag, and tell you what kind of SQL operation you will be used in SQL output. The second one is hardness value, and tell you how difficult it is about a SQL, and you will think hard or easy. Yeah, maybe we want the model to learn about that. And the third one is the correctness indicator. This is mainly for training purpose. So we would like to further separate the positive or negative solution or the SQL output. So I will tell the model to distinguish, you need to output the correct one or the incorrect SQL. So just for that augmentation. So when you're doing the inference, when we have the metadata ready and doing the inference, the correct indicator metadata type will always be correct, because we want to get the correct SQL, right? So after we define those metadata, query metadata, and the next problem is how we to do the NL2 metadata mapping, right? So yes, it's very straightforward, and we're using a multi-label classification problem, and we just frame this mapping as a multi-label classification problem and use a classification model to do that. And I would like to highlight here, because the classification model can be very simple to implement, right? So you can leverage any existing NL2 SQL models to implement the classification the model. So we can using any encoder derived from NL2 SQL model to implement the classification. So there's no any further code you have to write to implement the classification model. And after the decomposition, okay, right, we got a set of necessary or important query metadata, and the next step is to leverage all those metadata to do a more specific or more target SQL generation. So, so the vanilla NL2 SQL process is converts to a metadata conditioned NL2 SQL process, right? So we got some metadata enhanced, right? So we want to leverage those metadata to improve the whole process. Yes, yeah, and it's very simple, right? For sequence model, okay, I will be quick. And we will retrain those models by leveraging the actual metadata input. But for large language model, we don't need any specific fine tuning. We can only using the in-context learning to do to leverage the actual metadata, just like before. So it's very easy to implement. And after the generation, we got a bunch of, or a set of SQL candidates. So next one is to do the ranking. So we're not doing any translation anymore. Yes, because we have all the candidates. So we just want to fetch a best matching one to get the result. So ranking is to do based on the semantic similarity. So with the natural language and SQL counterpart. And we implement a two-stage ranking pipeline to implement. The first one is to for fast filtering to filter out those irrelevant SQL candidates. And the second one is to more specific ranking for top one selection. Okay, and we observed that most erroneous translation results or most erroneous ranking results happens on the second stage. So we analyze the problem, and we find the current ranking primarily relied on sentence level supervision to distinguish matched and mismatched the candidates. So we think it's not enough to do the specific ranking. So we enhance the ranking on the second stage, and to incorporate multi-grain signals into the training process to further improve the ranking performance. And we also, to support the multi-grain signal, we construct 3 different multi-scale losses to support that. For the first one is NL2 SQL global loss, which is the same as before. And we also decompose the SQL into phrases. So we do NL2 phrase losses, local losses to capture phrase level matches. And second one is phrase triplet loss to further distinguish positive phrase and negative phrase further to improve the ranking performance. Okay, and for the evaluation, so we conduct our experiments on two public benchmarks, Spider and Sign benchmark, which is Sign benchmark is a new benchmark, and I think, and have 3 real-world data sets. It's much more complex. And we use 3 different metrics to evaluate the performance. The first one is translation accuracy. The matrix is to check if the generated SQL is a syntactic equivalent as the ground truth. And the second one, execution. So no matter what kind of SQL you output, we just put into the database to get the result to see the equivalence. And the last two is for the ranking evaluation. So we do the experiments on 6 baseline, the 4 sequence-based model and the 2 large language model, and we demonstrate that MetaSQL can consistently improve all the 6 models' performance across the 3 different evaluation matrices. And we also do some additional experiments on the metadata sensitive analysis to further study the importance or the contributions for different metadata. So we find that MetaSQL is relative, not sensitive to the hardness value, but will exhibit greater sensitivity to the another 2 metadata. Okay, so quick conclusion for this slide, and we think metadata can bring some good hints for the auto-SQL problem, and we think cost to frame may be much better for the end-to-end approaches. And we also have another public paper accepted by ISD 2023, and also using the generated rank approaches. So just for your reference, if you are interested on that. So thank you.
Thanks, Yuankai. Any questions? Yeah, please.
Okay, thank you for this great presentation. I just have a quick question. You just mentioned the irrelevant SQL. So what's the concrete definition of the irrelevant SQL query?
Oh, okay. Good question. Thank you so much. And for relevant or irrelevant, we also evaluate on the semantic similarity. So how to distinguish irrelevant or irrelevant? We think we have to compare the semantic similarity. Because in the public benchmark, we have the ground truth SQL. So ground truth SQL will definitely be relevant SQL, right? So if we're using the syntactic equivalence to evaluate the translation result, so we think all the other SQLs will be irrelevant because we only have one ground truth SQL. But if we're using the execution matrix to evaluate the translation result, we will see if all the SQLs get the same result, we think all those SQLs will be relevant. So this is the result target oriented.
Okay, just a brainstorm question. Did you consider the SQL equivalence?
Yeah, this is it's very hard to determine the equivalence. So at this moment, we are using the equivalence tools published by those benchmarks. So they will decompose the SQL into different clauses and to compare the syntactic part, if this is equivalent or not. But for execution, so only the result will be the same. We think it will be equivalent. So it's much, kind of simple for equivalence.
Yeah. Thanks for your answer. Just a new angle. Thank you.
Thank you.
Thank you. And any more questions? Any more questions? Yeah.
Just one quick question. So you compared the sequence to sequence and the LLM. Can you think of any state-of-the-art use cases for a sequence to sequence model for ML-SQL still, since LLMs, as you said, are much more easy to implement?
So you mean, can you is your question? So sorry.
I'm just wondering if there's any use cases for sequence-to-sequence based NL to SQL now with LLMs.
Oh, okay. So I think the most more important factor is the cost. So if we want to lower the cost, we will use the sequencer model. And actually, for a large language model, if we want to fine-tune the large language model, will be much complex or much complicated for sequencer model. So in enterprise, actually, if you are not using an out-of-the-box large language model, we will suggest them to using a sequencer model. Again, you can specify the network architecture you want to either on the encoder side or decoder side. It will much more implemented. Thank you.
Oh, thank you. So thank you again to Yuan Kai for his great presentation, and let's welcome